So now the interesting thing about induction is that we normally do it on the integers. That is crazy. What's happening? Maybe you get a fluorescent light or something. So we normally do it on the integers, but we really don't have to. We could do it on really anything that you can list, right? Because the whole idea of induction is like if you can prove P of A, you can prove P of A plus 1, then P of A plus 2, P of A plus 3. It's like the domino effect. But really, it doesn't matter if all of these dominoes are integers. It just matters that we know how to get from one domino to the next domino, if that makes any sense. So what we really care about is that that our set's listable. So let's write down. Can really use induction on any set that is listable. Oh, it's blurry again. It's blurry again. Thank you. Oh, it does not have to be natural alpha. So we could totally use induction on negative numbers, right? That's why everywhere in the like the thing we just went over, the form, we just said for all integers greater than or equal to a, but a could have been -5, for example. Could have been -100. Could have been anything. So we can really use induction on any set that is listable. But I'm going to say, i.e., a set that can be made into a sequence with integer indices. And here's what I mean by that. Let's try to prove the statement, the claim for all x in D, where D looks like this. Maybe it's -3, -2.5, -2, -1.5, -1, -0.5, 0, 0.5, on and on and on like that. Yeah. So this is D. I want you to know that for all x in D, P of x is true. Well, here's the thing, right? These definitely are integers, and they're definitely not positive integers at that either. But there's a nice pattern here. So this D can really be put into a nice sequence, right? Like if we call this a 0, or actually let's call it a1. Let's call this a1. I'll do it in green or pink. So let's call this a1, this a2, a3, a4, a5, a6, a7, a8, on and on, right? This is like we put in a nice sequence like this. And so the point is, proving this claim would be equivalent to proving for all n in the set of, or all n in the natural numbers, P of an is true. Let that sink in. Does that make sense? Like if we prove that, like proving that for everything in this set, -3, -2.5, -2, that P of x is true, whatever this property is. Well, that means that for all n and n, P of an is true. It's because an, well, a1's this thing in D, a2 is this thing in D, a3 is this thing in D. So if we can prove the property is true for all of these an, we've proven it's true for everything in D. because D really just is the set of all these ANs. And then after that, the proof goes the exact same way. We'd say proof by induction on N. Yes, proof by induction on N. Then we'd have a base case. And that is let N equal to 1, because the first natural number is 1. So N equal to 1. And then here we want to show that P of N, which is P of 1, is true. And then we have our inductive step. And here we want to show that for all N greater than or equal to 1, our inductive step overlaps our base case. P of N implies P of N plus 1. Here's how we do that. Let N be any integer such that P of N is such that, or sorry, let N be an integer such that N is greater than or equal to 1. Assume P of N. We want to show P of N plus 1 logically follows. So assume P of N, show P of N plus 1 logically follows. Then, I don't want to go in the glare section, so I just say conclusion right here. Conclusion is that for all N and N, P of AN is true. Thus, for all X and D, P of X is true. I'm going to fix this slide. I'm so sorry about this. I did not think this would be an issue. And by the way, I messed up here. I messed up here a lot. All of these places where I have a P of N, I really want a P of AN, right? So I want to show that P of AN here is equivalent to P of A1 is true. And here I want to show that P of AN implies P of AN plus 1. And so here I want to assume the P of AN and then show P of AN plus 1 logically follows. Just because the property here, we're not working with integers, we're working with just whatever's in this sequence. But the sequence goes up by integers, right? Like we can identify everything in the sequence with an integer. Like the third thing is A3, which is -2. The fourth thing is A4, which is -1.5. So -2 and -1.5 aren't integers, but we can kind of list them. There's a first, second, third, fourth, fifth, sixth, seventh, eighth, ninth thing, 10th thing, on and on and on. Does that make sense? Yeah? The idea really is just use this idea of induction, of having the first thing prove the second thing prove the third thing prove the fourth, go up like that, the domino effect, except on a sequence rather than on just a set of integers. But it's really the same thing. Okay, well, no questions. Then we're gonna move it on. I don't even want to look at that crazy glare.